Simple harmonic motion is really cool, but it takes a little bit of practice to get the hang of this equation work. Um, kind of what it looks like. We're going to have a horizontal spring, and then attached to the end of it, we've got a mass. And this one I made up that the mass is 500 grams, and the spring has a constant of 18. From its equilibrium position, it doesn't matter which way we move it, it says pull, so maybe that's extending the spring. So we stretch it a little bit longer so that the 500 gram is 20 centimeters away from where it was before. If we do that and then let go of it, the mass is going to vibrate or oscillate. If there's no friction to steal energy away, it'll squish the spring up a lot and end up way over here, 20 centimeters away from where it started, but the other direction. Basically what's going to happen is this mass is just going to wobble back and forth over and over again. From a 20 centimeter position through its equilibrium to the other 20 centimeter position over and over and over again. When it's at its amplitude position, whether it's this one or the one on the other side, it stops for a split second. At that point, the spring is stretched as much as it can, or at the other point, squished as much as it can, as much as it gets. All the energy is spring potential. When it goes whipping through the equilibrium, all its energy is kinetic. For that split second, the spring isn't squished or stretched, so all the joules are kinetic. If it's somewhere in between, then it's got a little bit of both. It's got some spring potential and some kinetic energy. The first one in this particular question asks about its maximum speed. We've derived an equation for maximum speed, but really it just comes from conservation of energy. The spring potential it has at amplitude is equal to the kinetic energy it has at equilibrium. So the 1/2 k a squared equals 1/2 m v naught is a notation for max speed squared. If we rearrange that, if we rearrange that, we get v max equals, the halves are gone, we got to divide by an m, so we get k over m, then we have to square root it, and the a squared turns into a after square rooting. That's the equation that you'll be given on your equation sheets back when equation sheets were important. That's one we could have started number one with. Now it's just a matter of plugging in numbers. The numbers I made up was a k of 18, a mass of 0.5, and an amplitude of a. So plugging those numbers in, the k was 18, the mass when we put it in kilograms is 0.5, and the amplitude when we put it in meters is 0.2. Crunching that out, it works out a little bit nice. 18 over 0.5 is 36, so we have 6 times 0.2. That's a maximum speed of 1.2 meters per second. That's the fastest that 0.5 kilogram mass will go. That'll happen when it's whipping through the equilibrium position. The second part of this question asks how fast it's going when it's only 10 centimeters away from its equilibrium position. That's a conservation of energy question. We know the amplitude, so we know all the joules are spring potential at amplitude. When it's at another position, it's got a little bit of both kinds of energy. It's got some spring potential because the spring isn't at equilibrium, and it's got some kinetic because it's moving. So just straight up conservation of energy. We can cancel out the 1/2, and we can do some common factoring if we really wanted to, but at this point we know everything but the v. The amplitude is 0.2, the k was 18. I'm curious about when it's 10 centimeters away, so I'm going to plug in a generic s of 0.1 meters, plus the mass was 0.5 v squared. So I know all the joules are spring potential, that's why I can use that 1/2 k a squared. They're all spring potential when it's at the amplitude. We're at a midway point, so we're kind of like what I drew up here in green. I'm curious about a midway point, 10 centimeters away from the equilibrium, so I've got to tackle it with energy. A little bit of algebra, you can double check, flip-flop things around. I got an answer of 1.04. I double check the algebra, watch your order of operations. I'm optimistic that this is the right answer because it's a little bit less than the maximum speed. Had I got a number bigger than 1.2, I know I would have done something wrong, because in the first question we figured out that the max speed was 1.2. Every other speed has to be a little bit